Hello and welcome to another episode of Rustacean Station. I am your host, Alan Wyma. Today I'm with, I forgot to ask how to say your last name, but Armin. Maybe you can help me to pronounce your last name. I apologize. I'm American. I'm not Austrian. So he's an Austrian developer who's very heavily into Python these days. But you may have heard of him from another community, and I'll go ahead and let him kind of introduce that part to himself, or we'll talk about that later on. And otherwise, you'll definitely see his username, which is Mitsuko. So he's Austrian, okay, not Japanese. So, but that kind of got me confused before. But anyways, Armin, why don't you go ahead and kind of give a quick intro to yourself?
Yeah, hi, I'm Armin, last name Ronacher. So it's a very Austrian-German name. I have been doing open source for many years. And by doing open source, mostly just creating open source libraries or fixing other things in other people's libraries. In a former developer life, I wrote a lot of Python libraries. I wrote the Jinja template engine, the Werkzeug WCI library, which is sort of an implementation for common utilities to build web applications in Python. And then on top of all of that, I built Flask, which is a micro framework, also in Python. And then I also wrote this Click library, which is sort of a command line utility thing. And in 2015, I think, I started working for Sentry, and I've since done a ton of Rust. Most of the things that we are building at the ingestion part of Sentry, which is a cross-reporting system, we have Rust code. So yeah, I have a lot of exposure these days to Rust. I've been building some libraries for Rust, in particular the Insta snapshot testing tool, which is decently popular. And I have recently also started toying around with actually porting the Jinja templating engine to Rust, because I had a little bit of a need to render some non-HTML actually, but render some stuff. And so I have been doing this as well. Yeah. And as of recent, I'm just exploring a little bit serialization, deserialization again in the context of Rust.
So you missed Jinja? I didn't know if Jinja was really that good of a templating language.
I actually did miss it quite a bit because there are ports of it to Rust, but there is not one that has some of the features that I actually needed, which is sort of the expression evaluation. I don't know if it's a good language, but it has become very popular and it has decent editor support. And so if you want to sort of touch into an ecosystem that's already there, it's pretty good to go with something that already exists.
Yeah, but here's the weird part about Jinja is it's actually not Jinja, it's Jinja 2, right? Is there a difference between Jinja and Jinja 2 other than just, is it a version difference or is it really a big difference?
So the reason I had to name it Jinja 2 at one point was that Python doesn't have it didn't have a good way to install multiple versions of the same package. And so from Jinja 1 to Jinja 2, there were massive incompatible changes. And I didn't want to frustrate the people that already use Jinja 1, so I just renamed the package. And yeah, now it's Jinja 2 forever, which is kind of funny because at one point there was even like bumped the version to 3 and there's like Jinja 2 version 3. But yeah, it's sort of an historical artifact that's kind of hard to get rid of. So it's Jinja 3 now, Jinja 2 version 3. It's kind of funny.
Okay, you completely blew my mind because I'm aware of Jinja 2 and all this stuff, but I was never aware that I was under the impression that like Jinja was like abandoned or something, and then somebody came up with Jinja 2. So you're also part of Jinja 2?
Yeah, I made Jinja 1 and Jinja 2. And then I actually also made the PHP version of it, which is called Twig. And then someone else took over from the Symfony project, I think.
Oh, really? Twig is kind of like a port of Jinja 2 from Python to PHP.
It was not necessarily a port. It was like a PHP version of it that is a little bit different because PHP has different iteration. Things like arrays work very differently in PHP. So when I made it for PHP, it just was different.
All right, where do you get the names Jinja and Twig? I know a twig is like a stick, right? So I don't get it.
So for Jinja, it's a really terrible multi-level pun because I originally wanted to call this like a temple engine, like a template engine. And then there was already a template engine called Temple. And then I figured, okay, let's just find a nice temple that had something could make into a logo. And there's, if you have a Jinja temple, there's actually this logo from Jinja. It's like standing in the river. I think it's called, let me see what this is called. It's like I think it's called the Jinja Shrine or something like that. It's sort of terrible pun. And the Twig thing is there was a CMS at the time. I think it was a CMS or was a blog. I forgot what it was called. It was called Chirp, which doesn't exist anymore. And it was quite fun in how it worked, but it used just PHP for rendering HTML. And I was kind of curious, like, how much work would it actually be to build a PHP template engine? Because at the time, there was really only Smarty, which was an alternative templating system for PHP that didn't use PHP's regular sort of built-in syntax. And so it was mostly just like a weak project to try what you can do with it. And yeah, Twig just felt like it fit, because Chirp also had like I think at the time it had like a logo which was like a bird, I think. So it was just the bird sitting on the branch. That was the idea.
Yeah, because I've been working with a little bit of Twig and tiny bit of Jinja too recently. So now it makes sense why I can pick up Twig so easily, because I definitely played a lot with Jinja in the past. Okay, that makes sense. I don't know. There's some things I like and some things I don't like about Jinja. Like the filter thing is good and bad. It's just the only thing that's kind of weird about Jinja is like you have to have this special templating language rather than kind of just using Python already.
Surprisingly enough, like I actually figured out this it wasn't a great idea to have so much Python in it, because now that I'm trying to make this also work on different platforms, you run into sort of all these kind of leaky parts of it. Whereas like, well, the expression in it is like a Python-ish expression. So it, like when you have a dictionary, you get all the methods that a dictionary has in Python. But then it's like, okay, well, which method do you have if this is running on Rust? Which methods do you have if this is running on JavaScript? Because they're all different. And so then the templates are not very portable. So that's a little bit of a disappointment that maybe it leaked around a little bit too much. But that was also what made it so powerful that you can actually do. Because like if you look for Ansible, for instance, and not just Ansible, I think Ansible and Salt both use Jinja for configuration management. So you generate out YAML files to define sort of your deployment system, like which service should get out, which configuration should be applied, and so forth. And that uses Jinja largely because it can give you all the expressive power that sort of you need to do this kind of shenanigans. And so I guess if Jinja wouldn't have been as powerful, then it probably also wouldn't have worked for the Ansible use case. And my hunch these days is that since most people actually use React or other JavaScript things for frontend, Jinja kind of largely moved into the configuration space. And this is actually also the only reason I needed it for Rust, is because I had to generate some YAML configuration and things of that sort.
Okay, yeah. I mean, I know that there is some templating within Rust, but like maybe you can kind of talk a little bit about that and why you think Jinja is a good one to port rather than using an existing one.
So this also goes a little bit into like why I'm doing so much with serialization. So the challenge that you have with Rust in general is that it's a compiled language. And it's a compiled language that doesn't have a lot of runtime. And so a lot of the types that you have to do like interesting things, they just don't really exist at runtime. So only a subset of all the traits that exist in the Rust world can actually be dynamically invoked. So this concept of object safety. And so when you build something like a template engine, you kind of have to choose two very strong paths. One is that your template engine compiles a template down to Rust code. And so it can invoke a lot of stuff, but it basically works by compiling it through the Rust compiler. And so then you could have like a template that sort of embeds all of Rust or whatever you want. And that becomes sort of compiled into your binary. And there are a bunch of engines in Rust that already do that, some of which are Jinja inspired. And then the second option that you have is that you do everything at runtime. But then the challenge is like, how do you represent an object at runtime if Rust doesn't have this concept? And the way Mini Jinja does it is, it's not the only one. A lot of engines do this. They say like, okay, if an object implements serialization via Serde, then we're going to use their serialization system to transform this abstract definition of what the object is into a runtime representation of like a special object. And so in Mini Jinja, there's an object which is called value. And anything that serializes via Serde gets in memory serialized into this value object. And then the value object gets passed to the template engine, and the template engine can manipulate it. So it can say like, okay, if this value object holds an integer, then we can do additions with it. If the template object holds, the value object holds a hash map, then you can do indexing into it and stuff like this. So yeah, that's basically, it uses Serde to do this transformation into a runtime thing, and then it can evaluate this. It's largely based on the same ideas as Jinja. There are some small differences to make it work a bit better in the Rust ecosystem. It is unable to, there are no keyword arguments, there are no macros. There are some things that don't exist, but for the most part, it tries to stay relatively close to the original. And the idea is that you can do two things with it. One is obviously render templates. That's a pretty obvious one. But the second one is I wanted to enable the same thing that you do in Ansible and other things where you can use the template engine as an expression language. So if you, for instance, say like, okay, I want to filter all the, like, let's say you have like a command line executable that runs through every line of standard input, and then say it parses it to JSON, and then you want to apply filter expression and filter out everything that doesn't look like something, and then can use the expression language part of Jinja to do the filtering. And that's actually what I needed it for. And in that space, there wasn't that much in the Rust world, so that's why. But it's also like quite fun to build these things. So partially is definitely it's just spend some time to do something kind of approach.
So the thing that I was actually interested in about the templating stuff is like I'm so used to so many languages which when you deploy it, you have to have a bundle. So maybe your app code is kind of as one binary, but your templates would have to be like included with it. So actually when you deploy this thing, it's all just one single binary that you have to run, right? You don't have multiple files you have to put together.
You can choose how you want it. The default mode is that you embed the templates in the binary, because it prefers to load it from static strings, from static memory. But the goal was that you can load them dynamically at runtime too, because a lot of cases like Ansible configuration things, like unless you want to recompile your Ansible thing every time you do an Ansible configuration change, then like that's not going to be a lot of fun. So for a lot of use cases, you need to load templates at runtime.
Okay. Is that difficult to manage? I mean, because that could give you some unexpected outcomes if you're throwing templates in there that just aren't defined. Like basically some assignments.
Everything in mini Jinja is runtime. So if the template is not there and you actually try to load it, you will get an error. Likewise, if the template does something really stupid, that there's some stupid stuff you can do with it, like you can endless recursion and things like that, which like definitely don't do anything good if you try to do it. But that's just like not much you can do about this. Like somewhat Turing complete language. So obviously you can fuck it up.
Okay, so this is actually already complete then, right? We can find this on Crates.io?
Yeah, if you go to Crates.io, you can find mini Jinja and you can do some stuff with it. It's fairly compatible to Jinja. I use it a little bit, but on nothing published yet.
So mini Jinja, no creative name for this one this time?
No, just a small version of Jinja.
Okay. Was just curious. Yeah, I kind of want to talk a little bit more about like how come you got started into programming, right? I want to go a little bit more into your history to kind of understand, who is Armin and where did he come from?
Originally, I started programming, I think mostly just because I found a book. It's like, hey, you can teach your computer to do something. And then later, well, not much later, but a little bit later, I learned that PHP exists. And I didn't really approach PHP in the sense of like a programming language. So I learned a bit of Python before, and I found this to be interesting and stuff. But with PHP, and actually the first language that I used was Delphi or Object Pascal. With PHP was different because you could sort of create stuff that other people could see without them having to install it on your computer. So this idea that you could put something somewhat interactive on the internet was really quite interesting to me. And this was in 2004 or 2003. And around that time, the first public version of Ubuntu released, the Linux distribution. And because I lived in Austria, I got to know the German Ubuntu community at the time. And the guy that ran that website, he gave me SSH access to some modifications to PHPBB to make it a little bit more like specific, theme it and stuff like that. And that's largely how I got into web development, is like running and modifying this portal, which is called Ubuntu Users. We, over time, ported this whole thing to Python, wrote a wiki and a block aggregator and all kinds of stuff to it. And it was just a fun moment in time to build this because Ubuntu got relatively popular. It was sort of a rebellious thing to use Linux at the time. And to be a part of like building this community was quite fun. And that's mostly what got me into programming. And then because I built a lot of open source things to build this and other things, I just got to know more people that started using my libraries and so forth. And it's just sort of a self-reinforcing system. Well, eventually, like with the people that use your things, you get to learn more and get more interested in it too.
So is Python more of like I don't know, it seems like Python was something that you really love because that's just what you're really known for. And PHP was just a way to kind of, for your stuff to actually get out in people's faces. Is that kind of like what was happening?
So the reason I wrote so much Python was because like it was so easy to build PHP stuff and have it run there. And Python at the time, it was almost impossible to get it running on anything other than if you really knew your way around it. There was not even a standard between like the different versions to get it running in an Apache web server. There was a fast CGI, which needed an adapter, some of which was unstandardized. There was mod Python, which was really odd, not at all like mod PHP. And so that was actually what made me interested in WCI. It's abstraction standard, and I started building tools around it because I really wanted Python to have this sort of easy deploy story that PHP had. Because like that was really great with PHP, but PHP at the time was not a good language. PHP is a pretty decent language now, but at the time it was just not at all great. When I was using it, there was, I think it was PHP 4.2 or something. It was a very different language, and it was not a very good language. And so I really wanted Python to be popular in that space and more usable. And we built all kinds of stuff. We tried to build like a PHP replacement that's sort of open source and for others to use, but we never finished that. But yeah, just built all this stuff around it, including documentation tools, template engines, micro frameworks, and so forth.
I'm kind of curious about what, like, you started off with Delphi or Delphi, but then how did you go over to Python? Like, how did that come underneath your radar?
To be honest, the big reason for that was that it was impossible to build something in Delphi and have it run on Linux. That was sort of the end of it. So because I was already curious in Linux at the time, there was no version of Delphi that compiled to Linux at the time. There was sort of like alternative things that just were not popular at all. And I already knew that I wanted to build open source things. Not because I was like a super believer in open source, but because I recognized that if you build this in an open source fashion, then other people can use it. And that model doesn't work, or at least didn't work at the time with Delphi. I knew from the Delphi community, some people that tried to sell components for Delphi, but they had so few users and it didn't sound appealing at all. I knew that I wanted to build stuff for other people to use. And so that was just, that was the end of that, which is kind of a shame because Delphi was actually a quite nice language, but it just died by its distribution model.
But you saw Python as a much better alternative. I guess it was, I mean, even then when you started switching over to Python, it was already pretty much a lot more popular than Delphi or Delphi.
I don't know if it was necessarily more popular in all the communities because Python, when I started using it, was not super popular. It was definitely like on all the languages that existed, it seemed a little bit like the underdog because so first of all, on the one hand, you had like once you went out of the Windows ecosystem, there was like everybody had Perl at the time. Mm-hmm. It was like sort of the standard language to build like CGI scripts, or PHP, obviously, which was pretty big for web development. But then if you did like serious software development in open source, then you did Java or C. So Python was not maybe it was already popular. But the main reason actually that got me interested in Python was the fact that you could sort of also modify the interpreter. So you could open up the interpreter, the C source code, and do modifications to it and do all kinds of stuff. It was very transparent. It was very easy to modify everything from start to finish. And so for someone who was just curious about how computers work and so forth, Python was a pretty good target because you could just, like look behind the curtain and see what it does. And that was already very hard to do with PHP.
You mean for Perl, they couldn't do something like this? Or you never looked at it?
You could probably do it for Perl, but I never learned it. It was sort of like Perl was just not, it was already very complicated at the time. And it was not the language that sort of interested me. But Python was pretty straightforward. And also I had a book on Python that got even before the book on PHP that sort of explained like, this is how you can program Python. And it was okay. I mean, it wasn't super interesting at the time when I read the book, but since I already knew, it's like, okay, which language works on Linux? Okay, there's C. It's a little bit hard for me right now. PHP, I already know this, but I can't build stuff that's sort of outside of the web. Okay, what else is there? Python was one then.
It's kind of funny though, because you want to look outside the web, but at the same time, you brought a lot of things to the web, right? I don't know how much your impact is in terms of starting that all up, but like maybe you could talk a little bit about that because I know you joined some kind of, or you guys made up some kind of group. I think it's called Pocoo or
so it's like
or something. Mm-hmm.
Basically at the time. So when we built, there were a bunch of us who built this or maintained the German Ubuntu community's online presence. And we had this really weird idea. Let's just try to build this in Python instead of PHP. And for that, I started an IRC channel. I was like, hey, who wants to join in this on this one here? I've already started some things. Let's build a forum software, like a bulletin portal. And we called this Pocoo. And a friend of mine, Georg, joined in, and We never finished this thing that we wanted to build, but we tried to build all kinds of other stuff. Plugin systems, we built templating engines, the web frameworks. The Sphinx documentation tool came out of this, the Pigment syntax highlighter. Like everything that was needed to build a web forum without building the actual web forum. That we never did. Or at least we didn't finish it. There's still source code around somewhere if one can find it. And the idea was really quite funny at the time because in PHPBB, everybody used to have these patch files for plugins. So you downloaded PHPBB and it was like this web bulletin board. But if you wanted to add a new feature like file uploads, for instance, which were not supported out of the box, you got this like instructions about like go to this file, edit this code, and then go to this file, edit this code, go to this file, delete this code, and so forth. It was like a manual patch process, how to modify PHPBB to do this thing. And we wanted to build this on a plugin system. And so a lot of this motivation was like, how can you build something like this? How do you build a plugin system to make this work? And there was actually a software at the time, I think it was 2006, 7, I don't remember quite, it was called Track. TRAC, which was like an online self-hosted version of GitHub, basically, where you can do your own source control, issue tracking, and so forth. And we also wanted to build some of the things to fit into that because they had a really nice system where you can modify it. And so they eventually started using Jinja and the Pigment syntax highlighter there, which was a nice side effect. But it was not the original goal to build this.
This thing is, it sounds like you got too busy shaving the yak that you never got to the next step, right?
Yeah, but it's not that we didn't go, because we actually did finish this forum, but it was never open sourced. If you go to Ubuntu users, the .de, which is sort of the German community, the software that runs there is actually, I still wrote the original version of this. It's like this, and it's written in Python, but the source code is just too embarrassing to open source. And so a lot of it just stayed that way, which is kind of funny also for being an open source community.
I'm guessing there's no tests for this?
I don't know anymore. I don't even know if I could get source code access if I would try to figure out how to do. But it was quite fun how it was built. It has a lot of, especially the wiki has a lot of really funny sort of architectural decisions. And I found it quite enjoyable to try different kinds of approaches. So I think it had some tests.
So this is it's called Inyoka, right? That's the name of the engine?
Yeah, that was the name of the engine, but it was not open sourced.
All right. So from this organization you guys created like a tons of stuff, right? You said Sphinx is huge. I think Sphinx inspired a lot of other documentation stuff out there. Yeah, Flask, which is we're talking about before the show. Yeah, I'm actually using now in a project. I'm slowly getting rid of it because it's killing me. No, nothing against you. I think it's just a Python thing. I mean, I'm having high concurrency issues, so I have to reach for something else a little bit more fitting to that problem. And yeah, I mean, all this cool stuff, like, I don't know, like, I mean, it seems like you're really enjoying your time in this community, right? Of course, I'm happy across to the other side, the good side, the more fun side. You know, what kind of like happened, right? Because I think if I remember correctly, and let me know if I'm wrong, I think you were already at Sentry and you looked at, or somebody looked at using Rust for some pieces because Python, I think, was just not standing up to it. Because I think Sentry in the beginning was actually 100% in Python. Is that right?
Yeah, so I don't know when I used Rust for the first time, but it was really early. I remember I did a talk Rust. I think it was like 2012 or so. And I was already using Rust like in 2011 maybe, but not in any real capacity. It's just like, hey, this is really interesting what they're doing. And the funny thing is that Rust at that time was a completely different language. It used like Ruby style iteration, a whole bunch of stuff. But it was really curious how it worked, and it seemed to be on a pretty decent trajectory already at the time. And so I just kept playing with this over the years. And then in around 2015, I think, we had this problem at Sentry where, well, the order of how it happened was actually I already built a library in Rust for processing JavaScript source maps, mostly just as sort of a debugging tool and just to see like how is it to work with JSON in Rust. Because source maps, I don't know if you're familiar with them, but they're pretty large JSON documents that contain mapping information for how to go from minified JavaScript to unminified JavaScript. And the odd thing is that Sentry is a crash reporting tool. So you send a crash report and you can see it in the UI. That's more or less what it does. And the crash reports were originally, they didn't require any processing on the server. It just got a JSON dump from the client and you more or less put this straight into the database. And the UI could then do some shenanigans on it, like show you the Stacktrace in a nice rendering. And it could also do grouping based on similar Stacktrace frames. The challenge with front-end JavaScript was that eventually these started getting minified, and the minification was unstable between builds. And so in order to get this stable grouping going, you really had to apply the source maps on event ingestion, which meant that every single JavaScript event that went in required to have its source map applied. And with increasing number of customers and increasing number of JavaScript events, because JavaScript was getting more and more utilized on top of Sentry. So we used to have like 90% Python, and then it was eventually, I guess, I don't know, like 90% JavaScript probably at the time. There was just a lot more load to this system to apply these source maps because that was all done in Python. And parsing some of these source maps required allocating like a gigabyte of memory just to have like this entire source map there. And so the only thing you have to do in a source map is parse the JSON, then do like lookup for like, here's line number and location, and then this new line number and location. And so since I already had this Rust library for source map processing, I was just like, okay, let's just build a Python extension written in Rust that just does the source map loading. And it was dramatically faster because it didn't have to do any of this allocation business. It just scanned through the JSON, deserializing what it needs to do at the time. And then, well, I think it might even have allocated a lot, but at least it didn't have to allocate individual Python integers and stuff like that. So it was just dramatically faster. And that was one of the two introductions of Rust at Sentry. The other one was the command line tool that we built. And that we did because Python was a pain to install on end users' machines. Because if you build a command line utility in Python, then you can't just give it to someone. You need to provide a way for them to install that and Python and everything with it. And so having just a single binary was really convenient. And so those two things were the start of Rust at Sentry. I mean, there's still like the vast majority of Sentry is Python, and that's probably not going to change. But all of the ingestion pipeline is having more and more Rust in it because with the event volume that's coming in, it's a pretty decent language. I don't know if it's the best language to choose for the job, but it's just the one that we chose, and it has been pretty good at doing the things it does. So, yeah.
So I'm pretty interested to hear more about this. Like, I mean, mixing the two different languages, I mean, it's been done before. It's still being done all the time, right? So what do you think what are the benefits of Python that you get, and what are the cons of Python? And then the same thing for Rust when you're mixing these two together.
So the one thing that Python was always really good at, and mostly as a historical accident, was that it was already such a slow language, like objectively slow, that the per every operation overhead was so significant that it didn't matter anymore if you made it a little bit slower. And it was still fast enough to do certain things. And so the little bit of thing on top that made it slower was runtime introspection. And that was actually what started Sentry as a business, because Sentry really was a tool to get crash reports for Python before it was crash reports for anything else. And the crash report you get out of Python is perfect because not only do you get stack traces, you also get local variables. You can introspect the entire interpreter state. And because the interpreter is so straightforward, in quotes, so slow, there's no JIT to destroy or anything like that. The cost of doing all of the stuff on top is negligible. There's not much anymore that you have to pay in additional cost. Which means that if you build a web service in Python and it's good enough, then it's also fast enough with runtime introspection, and you get really good operational behavior. So you get the good observability, or whatever the fancy word is that you want to use for it. You can see what it's doing. The garbage collector is barely active because most of it depends on ref counting. And so it's very predictable, maybe not very fast, but you can see what it's doing. That doesn't apply to a lot of other languages. Some languages are heavily dependent on the garbage collector. And then languages like Rust, they are completely non-introspectable. Like the Rust service that's running, probably it works pretty stable and you don't have to look at it much. But once you have to figure out what's going wrong with it, you're like in a world of pain because there's no way for you to attach to it and see nice things. And so that's why a lot of Sentry will always be not Rust, because there's like third-party integrations, there is like a lot of data munching of completely random stuff, and to figure out what's going wrong, you really want to have this ability to look in it. And maybe languages like Go can go into this a little bit, because Go has a lot more runtime there that can help. but Rust is just optimized for a very different case. And so that makes it not the ideal language for this kind of thing.
That's got to be one of the most unexpected answers I've ever heard in my life for any question. The fact that something is so slow, if you make it slightly slower, it's still okay.
Yeah, but this is the funny thing is because like I actually made a talk about this a couple of years ago. It's like one of the hilarious challenges that we had at Sentry is that we build a product which set expectations, right? So there's a Python Stacktrace and there's a screenshot prominently on the start page and you see local variables, right? And then it's like almost any other language doesn't have this feature, right? Because it wasn't optimized for that. And particularly targeting certain languages like C++ puts you in front of a really huge challenge because people write C++ code largely because they want something really, really fast. They take any optimization possible, right? And so if you add this overhead, like that was insignificant in the Python code, and you put this now much more significant overhead in the C++ code, then the entire argument for writing in C++ is now gone, right? Because you just made something not just 10% slower, you probably made it like 100 times slower for adding this runtime thing. And so once it's already that slow, nobody picks C++ anymore, right? Because like, if it's that slow, I'm going to write it in Java or something else. And so the crash reporting infrastructure that we're building for C++ at Sentry, for instance, has to deal with the fact that everything has built to make it as painful as possible to do a runtime introspection. Like even stack traces from C++ are just barely functional because C++ is not optimized for giving the most basic stack traces. And it's quite frustrating to do this. But yeah, it's like the expectations that it works. And so we're just building crash reporting for C++ as well, obviously. But you're going to always get better stack traces from Python and some other languages.
I think Ruby has something similar, no? For this kind of thing.
Yeah, Ruby is also incredibly slow. But the funny thing with Ruby is that it has this huge dependency on two parts of it. So the first one is that it has a very active garbage collector, like there's a mark and sweep collector in there. So there's no rough counting. So you're dependent on the garbage collector a lot, which makes it less fun to operate than Python. There are people that operate Python with the garbage collector disabled entirely. Just turn it off. And then if it eventually uses too much memory, just restart the process. But the other thing that Ruby has, it has this very weird interpreter internals where there's a lot of goto and a lot of long jump for exception handling. And so the introspection of the interpreter state in Ruby is actually very expensive. I tried to do this a couple of years ago to get local variables going for stack traces in Ruby. And doing that just completely killed performance just because the interpreter state in Ruby wasn't set up for this kind of stuff.
I'm kind of curious, though. Do you know why this was all set up before? Was it just something that was just planned from the beginning with Python?
That you can access the interpreter state?
Exactly.
I think it's a good question. I think partially it's because Python had from the start this really odd relationship between the C code and the Python code. And so every once in a while, the people that built some of the features in the language were too, like, I wouldn't call it lazy, but they felt like, okay, I can actually write this in Python now. I don't have to write it in C. And so every time they wanted to write something in Python that required access that you otherwise would only get in C, they exposed it so that their little Python code can access the C stuff. And so, for instance, the exception rendering in Python in parts uses a system called line cache. And line cache is just a huge, I don't know if it works this same way today, but at the time it used a system called line cache. It was a Python module where it said like, hey, I have this file. Please give me the source code for this file so I can render it in a stack trace. And that was written in Python. It wasn't written in C. And so the exception stack trace rendering wanted to show the line, the source code line. So that used line cache. And then eventually it started using a lot of Python to render the stack trace. And so for the stack trace to render, it had to access interpreter internals. And so they had to expose that. So I'm thinking that for the stack trace rendering, which was written in Python, they probably had to expose this from the C layer so that they didn't have to write it in C. That's my hunch of what happened, but I didn't actually do the investigation. But that's just what happens a lot in Python is that people started exposing interpreter internals so they can write stuff in Python rather than in C.
Okay, that's interesting. How about with Rust, though? Because, with Rust, you can see stack traces. I guess that story is different than it is with C and C++ now.
So the funny thing with Rust is that you can actually get relatively decent stack traces out of it, but it doesn't use the language for that. Stack traces in Rust are actually using these days a library called Gimli, I think. Or is it Goblin? There's a library called Goblin, one is called Gimli. I always mix them up. And they use stack walking like any C++ library does. And where a lot of people used to use libunwind and things like this over the years, now the Rust developers wrote their own, or the Rust community actually wrote one, which now also Rust uses. And that's actually the same one that we're using at Sentry for C++ stack traces. So there's a nice little sort of circle that closes there, because the fact that you can get really good stack traces nowadays with Rust tools, not just for Rust, but also for C++, is really nice, because we were heavily dependent on using C and C++ libraries for this. And now we can use Rust libraries, which are much easier to maintain, improve, and also a lot more stable. Our crash report handling at Sentry by using these other libraries like Breakbed is highly unstable, because you put a lot of binary data into it and it doesn't really work. But the stack traces in Rust are built entirely through walking the T-stack. There's no built-in support in the language that makes it easier.
But I think within Rust, there's actually a small runtime or something. Am I wrong
There's
about
a small
that?
runtime, but so one of the problems that you have with stack traces in a native language is that in Python, every time a function calls another function, you push something on the stack, and that sits there in the interpreter state, and you can just iterate through it, and you can what's the function name, what's the location where I am, and so forth. With native code, if you have a small function that calls another small function, there's a good chance that the compiler will say oh, I'll take the entire small function and I will copy paste it in there, and I will just inline it. And now if you try to make a stack trace, this inner function is invisible, because it just copy pasted the entire code there. And so the only way to reconstruct this is to go into these debug information files, these dwarf files or PDB files, and evaluate a really complicated inlining system that tells you, for the location where you are, this is what the function used to call. And so when you want to render a stack trace in Rust, for instance, in the first step, it will walk the stack and it will give you function by function by function of the C stack. But then on symbolication, it will go for every single function and will go to the debug information files and try to figure out, was at this location an inline data function that I need to show? So if you do vector push, for instance, the vector push, if that fails for some reason, that will never be a function call, that will always be inlined due to what the Rust compiler thinks is reasonable. The same with destructors. And destructors, for instance, are a pretty big problem, because destructors love to crash for one reason or another, and then you don't see them in the stack trace. So the stack trace in Rust doesn't actually come from the runtime. It comes from relatively close operating system internals. So depending on which platform you're running on, Rust follows the same rules as C and C++ for stack traces, for calling functions, and then for generating stack traces. So it's not actually the runtime that gives you this. It's just the computing architecture has some rules about how stack frames function, and it does that. So if you're curious in this, it's a library. There's an entire ecosystem of stack trace producing libraries in Rust, which are very good. But they all support not just Rust, they also support C and C++, because this is the same system.
Okay, yeah, that makes sense. I mean, they do get compiled onto nearly similar kind of bytecode, right?
It's not even bytecode that runs that. It's just native instructions, CPU instructions. And the other reasons that has to work this way is because Rust code is really built interoperate with other languages too. So if your stack trace would stop functioning because your Rust code calls into C++ or into C, and that code crashes, then you wouldn't be happy either, right? So you want to have this sort of bidirectional compatibility between them. And so you, hypothetically, Rust could work differently. And so screw the operating system, I'm going to build my own stack traces. And that's kind of what Go does. Go decides to do everything itself, and then Go runs into all kinds of challenges when it tries to work together with the wider ecosystem, because it does everything its own way.
I think we can come back a little bit more to the Python and Rust part, right? So a lot of people write in Python out there. It's a pretty popular language. I think it's definitely one of the most popular, if not the popular language out there. Rust is the most loved and maybe sometimes also the most hated language out there too, because of all the very steep learning curve, right? When you're putting these two together, I think you're using the very standard kind of library, right? I forgot what name that was. Pio3, is that right? Using that one to do everything?
We don't, but we will probably. When we started writing Rust and Python code together, there was still a lot of Python 2 at Sentry, and there was no stable ABI, it was called, yet. Stable ABI means that I can compile a binary to a Rust binary into an extension module that can run on multiple Python versions at once. And that's what Pio3 uses. But that didn't exist yet when we started doing this. So we wrote a library called Milksnake, which is just a tiny wrapper around setup tools. So you can compile a Rust library just to a C extension module, a C object file or a dynamic linked library. And then we used CFFI to load this at runtime. And we had some tools around this. And this is actually still what we're doing, but nowadays we're actually writing a lot more services. So most of our Rust code talks to the Python code via queues or HTTP, like Kafka or RabbitMQ or just HTTP code. And there's less in-memory exchange, although it still exists, but a lot less. And we'll probably use Pio3 for this in the future, but we haven't made this change yet.
How is this for your clients out there? Because if I remember correctly, maybe things have changed. Sentry is also, you can actually manage your own self-hosted one, right? Is that still the same?
Yeah, it's still the same. So you can still self-host it. It has changed over the years. There's effectively everybody runs Docker now. So you don't ever see anything anymore because you just install it from Docker, and all the ugliness of making different things fit together is just hidden in a container.
Oh, are you guys completely over to just handing out Docker container images and just saying, run that? Or is there actually bare metal instructions?
I mean, hypothetically, you could still run it without Docker, but we removed the documentation for that, I think. I'm pretty sure there's no documentation anymore for how not to run it with Docker because it's just a lot more variables that can break. And it's already hard enough to operate Sentry these days because of all the different services that you need to run to make it provide all the features that the system has these days. So it's just Docker containers now.
The reason I'm asking is because it seems like every computer out there, especially for a developer, you have a C compiler, but not every computer will have a Rust compiler. So I was curious how you guys handle the situation.
We're actually dealing with this constantly because we have a lot of developers, many of which only do JavaScript and Python. And so they don't want to compile all the services that they need to have. And so we use almost exclusively GitHub Actions to build stuff. And we actually built everything that we need for the developers' machines. So if you start Sentry locally, the Python server, and you need to use, for instance, the library that talks to another component that's written in Rust, you can pip install that library, and it will give you a binary specifically compiled for an M1 Mac, for instance. So we do redistribute them for internal use. And this is also how the Docker container gets to its binary, so nobody has to run the Rust compiler. That's why we wrote this Milksnake thing originally, because it lets you install a wheel, which is sort of this pre-compiled Python thing that contains the right architecture of your Rust code. But if it doesn't find that, because, for instance, when we switched over to M1 machines, we didn't have M1 binaries yet. And then it fell back to compiling from scratch, which can take a bloody long time for large dependencies, which is a bit of a shame.
Can you talk more about that? Because I do remember wheels, and they're very simple to install. It's a WHL file format.
It's just a zip file that contains all the bits and pieces for Python. So it's a .py file also in there. In case of our libraries that are written in Rust, that SOs in there. And then we use CFFI to load them. It's just Python just unpacks them, puts them somewhere, and then it can load it without having to run code at installation time. It just unpacks them.
Let's say I'm doing my core Rust stuff, and I want to just hook it up to Python because I want somebody to use it in Python or whatever, right? Maybe my clients ask me for that. If I want to support Linux, Mac, M1, x64, Windows, all this kind of stuff, what's the setup in order for me to do all this kind of stuff? I'm just curious. I think other people may be curious too.
So the closest thing to not hating that experience at the moment is an extension to Pio3. I forgot the name of it. But Pio3 basically lets you do things. It lets you use Python from within Rust or Rust from within Python. And if you want to use Rust from within Python, you can redistribute this. And I think the tool is called Maturin or something like this. But it's basically a build tool that helps you build wheels that you can then upload to PyPI and give to other people. That's more or less how you would do it. And Pio3 is sufficiently easy to use that you can relatively trivially build Rust libraries for Python. And in fact, even some very popular Python libraries use this now. Like the Python cryptography library is partially written in Rust now, and it uses Maturin, I believe. I'm not entirely sure if it uses Maturin, but it definitely is written parts in Rust, and it redistributes wheels. So there's an ecosystem that you can utilize to do this if you want to.
Okay. Yeah, I think I remember this. I think I remember recently we had one of the guys over here. Actually, I'm the only one in my dev team using Intel. Everybody else is using M1 over here. And I remember everything's working fine on my machine, but I think we had an old version of the crypto library and it was just crapping out on M1 and it was super painful to deal with.
Yeah, it's unfortunately whenever there's an architectural change, there's a little bit of pain.
My life is pain, to be honest. I always go through all this kind of like initial stuff, and then once I figure it out, then I kind of easy to fix everybody else's problems, but that's okay. Whatever doesn't kill me makes me stronger, I think.
Yeah, that's unfortunately how programming works these days. It's a constant shifting ecosystem.
All of them. I think the biggest pain for me is usually always still Node.js and NPM and all those packages. It's like every week I have to upgrade all of my Node packages because they no longer work with the newest version of Node for some stupid reason. I don't know what's going on. Backwards compatibility just isn't a thing in the JavaScript world or something. I don't know. But anyways, enough kind of complaining. I think we could start to kind of work towards the main topic, right? So you mentioned based on the original problem that you're trying to solve, like you guys really had you work a lot with serialization, and I guess the thing that you guys are looking at from the beginning probably was Serde, right?
So we both at Sentry and within a lot of the libraries that I wrote, both the insta snapshot testing tool, the mini Jinja templating engine, I use Serde. Serde is a shockingly good serialization library, I would say, and it's very, very stable. So it has, when it hit Serde 1.0, which was a massive milestone, from that moment on, there hasn't been breakage anymore. So the ecosystem supports this everywhere, which is really good. And so the good thing about Serde in particular is that it's at the cost of higher compile times, it generates very efficient deserialization and serialization code. And this is particularly good when you serialize a lot of JSON. And the way it's built internally also lets you target what's called non-self-describing binary formats. So a self-describing binary format is one where you just need to load the document that you're getting, like a JSON document, and without any other knowledge, you can fully parse it. Like you can tell what's a key and you can tell what's a value in a dictionary just fine. And non-self-describing format doesn't have that property because everything is just lying one byte next to the other byte. And without knowing which byte is which, for instance, the first item is like a key and the second item is a value, and they might not even know what the first and the second value is because they just look like bytes lying next to each other. You can't parse it. And Serde can support both of them. The challenge that Serde has, I think, there's a range of challenges that we discovered over the years about Serde that are kind of unfixable without a major upgrade to Serde. And some of these we have successfully worked around. Some of them we almost entirely built a system around Serde. And yeah, and recently I mostly started thinking like, hey, what if Serde would actually work differently? Could you address some of these shortcomings? And that's why I started this sort of deser library just as an experiment to see what could an alternative serialization system look like for Rust. In that space, I'm exploring a little bit. So some of the challenges that Serde has today are, one is a relatively fundamental one, which is that Serde has a maximum depth of input. So whenever you enter a new nested structure, you're putting a level onto your call stack. So if you have like 200 lines, 200 deep JSON structure, deep thing, you might start running into recursion limits on Serde. That doesn't sound like a massive problem because who has documents this deep? But it actually, unfortunately, does come up in practice a little bit. So that's one of the things that I wanted to see how you can address this. The second more fundamental one is that Serde's data model does not support data that's not native to the Serde data model. So the Serde data model can support integers, it can support strings, it can support sequences and objects. But every once in a while, you get some data that doesn't fit into the data model, and then weird things happen. So for instance, if you have, let's say you have a JSON document, and the JSON document contains big nums, so numbers that are larger than a U128, like a 128-bit integer. the only way that you can use this to represent in Serde's data model is a string, because the largest integer is 128-bit large. The way, and then okay, so how does a JSON parser deal with a number that's larger than 128-bit? And the way Serde does it is that Serde JSON, when it encounters a large number like this, and you have a special feature enabled, then it will actually encode this number as an object. So it will start an object with a special internal key, like it will start like a dictionary key underscore Serde underscore something, and then it puts the large integer as a string in there. And this is sort of a very basic example of in-band signaling. So you use the format to in-band signal other stuff, as opposed to out-of-band signaling, where you would carry this information away where the original source document can't use it. Because one of the challenges of this is that once you know that this is how Serde encodes stuff, you can also craft some input as an external party that looks exactly like this. And that's not necessarily always a problem, but that's problematic in some ways. So an example of where Serde sort of does weird things that most people don't realize is that if you implement deserialize in a struct with 3 keys, let's say it's a point X, Y, and Z, and you use like struct point, and you implement deserialize. In JSON, it's represented as an object with a key X and the number, key Y and the number, key Z and the number. And so it's a classic object, and it serializes and deserializes in this object. But because of how Serde also supports non-self-describing formats, you can also send an array with 3 integers, and Serde would happily deserialize it. And so every single object in Serde also is representable as an array, for instance. And that means that if you have an API that accepts a struct as input parameters, every single API that you write will also start accepting arrays, which is surprising, I would say. And so it has all these sort of weird kinks in it. And addressing them in Serde itself requires a major revision and major changes that will break the entire ecosystem. It's not easy to get this into Serde. And so I was just trying to play on the side with this.
Have you actually tried to bring this up to the team or made an issue about this to see what they think?
Yeah, I mean, it came out, it's like I wrote a couple of years ago, we needed a special feature in Serde that we use at Sentry, which allows flattening of structures. And I wrote this feature for Serde, and I committed it, and I got it upstream into Serde, but I had to pick a very odd design to implement this feature, which requires internal buffering. And I could only make it work for JSON. So it doesn't work for any other format really well, which is okay enough for our use case. But because I wrote this original thing, and I also opened up the follow-up issue on GitHub was like, hey, this doesn't work because of these limitations. I sort of see the activity on this issue of like all the other people bumping into this. It's one of the most active items on the Serde issue tracker is this sort of this limitation of the data model. And the developer of Serde knows about this problem. And I think he also wants to fix it. But the fixing this problem is not trivial and will definitely break some ecosystem. Potentially, unless someone finds a really nice workaround for this. And so for now, it just stays unresolved because maybe the pain of it is not high enough yet to break the ecosystem.
Yeah, I was just thinking, what if there's some kind of way that you could turn a flag on or something in order to get this specialized behavior or a feature flag or something so that you could handle this better. But you're saying that's not even going to be enough.
Yeah, it's a very hard problem to solve because of everything has to be there at compile time. And the Rust language doesn't have enough expressiveness at compile time to make this sort of distinction. So like in Python, this problem wouldn't exist because at runtime, you would just say like, hey, am I in this special flag? And I'm going to do this thing instead. But here, this distinction has to be made at compile time. And so one type would have to inquire another type if it's in this old or in this new behavior. And this doesn't work today. This would require specializations, which are not a stable Rust feature. That would be one way to solve it. It's not the only way to solve it, but that would be one way to solve it. And the thing with Deser is that I don't even know if it's going to turn into a real library that should be maintained or used. I just mostly want to explore what do alternative approaches look like? Do they make sense? Right now, for instance, I know that my approach is very slow comparatively. It's like 3 times slower as Serde, but it compiles much faster. So there's some trade-offs in it. And it tries to see if some of these approaches work. And if it turns out that they work, then maybe this is something that the future Serde version could in parts incorporate. Maybe it doesn't make sense, right? But I felt like I have used Serde long enough now that I want to just make a little playground on the side to see what could a hypothetical alternative design look like for this. Because one thing that's kind of surprising is Serde is rare in the sense that it's a non-standard library module. It has zero competition, which probably speaks for itself, right? But typically when you have something like this, there is at least one competing library. And Serde has an absolute monopoly right now on serialization, deserialization, which is good, but it also makes it kind of hard to try to innovate a little bit in its space. And so I figured it's a good time to try something else.
I mean, you could say similar things about Tokyo too, right? I mean, it's not probably as monopolistic as Serde, but it's definitely it's hard to choose something else because everybody else just provides support out of the box for it.
Yeah, and I think this is good. I think that there should be, like, for languages that are coming up, and Rust is still in that space. I think monopolies are great. Temporarily monopolies are great. Like the 2 or 3 or 4 years where something should be a monopoly and external life should be a monopoly, so that everybody can rally around it and then figure out what are the problems. Because if you start with like this idea that, okay, there has to be competition from the start, then you're just going to have like 3 or 4 competing things, and none of which are actually innovative. They're just a little bit different. And like async STD and Tokyo for me are largely this, because they're kind of the same. We unnecessarily split the community in half to have 2 almost the same libraries. And there's not a lot to learn from that. So it's better, I think, for Tokyo or Serde or Chrono or libraries like this to get like 3, 4, 5 years of everybody trying to use it until everybody learns what the challenges are, and then the challenger comes to try to resolve these, rather than like splitting the ecosystem from the start.
Yeah, I mean, I can see what you're trying to say. I mean, I do agree that makes sense. It is nice that when you come to a community, it's like, what do I use for this? Oh, this is already here. Okay, what do I use for that? Okay, this is people are using. As opposed to you come to, I don't know, I'm trying to think of something that has a lot of competing.
Python web frameworks. I mean, there was never a time
Okay.
when there was a single one.
I mean, to me, about Python web frameworks, it's like, well, if you want a full-featured one, you go for Django. If you want something minimalistic, you'd go for Flask. That's always been my understanding. And there's nothing else out there that would even be in my mind. At least that's the way I see it.
I don't know if it's still the case, because now you have all these sort of API-only frameworks like Fast API. But when it started out, then it was even less than that, because what you had was basically like no framework was big. Maybe Django was about to become big, but it was just tiny, tiny libraries. And there were like every single somewhat popular Python web app had its own little abstraction layer for talking web. There was the Moin Moin Wiki, which had its own framework. Track, which was this sort of bug tracker, had its own framework. The first couple of websites that were written in Python, they built their own things on top of either Fast CGI. There was a library called Floop or Mod Python. Or Zope was there. Like, there was a ton. And that actually hurt Python a lot in the web for a long time, because they were all completely independent ecosystems. You had to pick one. And then on the other side was PHP. And it didn't matter. Everything was on top of PHP. That's like, maybe there was a framework involved, but it didn't matter because everything was compatible on this very basic PHP layer. In places where compatibility is needed, it's a problem. Because, for instance, if Tokyo has a competitor with async STD, then they are not compatible. So you would either have to build an abstraction layer to make them compatible so that you can use both of them at the same time, or you have to pick and choose the winner. And with frameworks in Python, it's largely that everything had to be built n times for every single framework. There's like an ORM that works with Django. There's an ORM that works with Flask. There's an ORM abstraction layer that works with Flask. There's authentication that works with Django. There's a different authentication that works with Flask. All the attempts of standardizing on top of WCI largely failed because the abstraction layer was just on the wrong layer. Yeah, it's hard. And so I think it's like, for growing things, it's better for a community to rally on one thing for a while. Not forever, but for quite some time.
Well, that's why I think you need something like, I think is it WCGI? Is that the one that's for Python? I know the one in Ruby is Rack. We have kind of like, there must be something. Is that the same thing, WCGI for Python?
So WCGI is this thing for Python. And it was sort of the first, I think, attempt of making sort of a high-level one. I was one of the people that pushed very hard for this thing to be like used by people. And it wasn't very popular for a long time. I even had to go to other communities to sort of propagate it a little bit. The guy who wrote the rec specification for Ruby, I poked him at the time. It's like, hey, consider doing this, because there was huge opposition in the Ruby community for something like this. Seth Shaw, he maintained a server which is called Mongrel, and he hated the idea of rec because he wanted everybody to use Mongrel. So he didn't like the idea that there was sort of like an abstraction layer to make compatible. And so I actually talked to his name was Christian Mankirchen. I think it's a different name now, but he did the version for Ruby, the rec one, and I even gave him a logo for this. This terrible rec logo is actually mine.
Oh, you made the rec logo?
Yeah, I made the rec logo. Sort of
oh my goodness! I feel like you're like a puppet master in my programming world because you have your hands built in everything.
Like secretly scheming behind the scenes to make stuff work. But that is like the cost of it is making this abstraction, and neither WCI nor rec ever worked good enough to be abstraction that was needed to allow things like authentication middlewares to work against multiple languages, right? Sorry, multiple frameworks. And I think it's the same with almost everything that has to work together. Like I couldn't come up with an abstraction layer between serialization systems. It just wouldn't. I couldn't think of what this would even look like. Like if hypothetically a new version of Serde or Deser or whatever becomes popular, then you're going to have a fractured ecosystem where half the system supports that and half the one supports the other. And I'm not looking forward to something like this.
I don't know. I can't imagine us having some kind of rack-like or universal-like API for different serialization libraries. I mean, we're supposed to be agnostic when it comes to like the futures and stuff like that, but it seems like you're just not for whatever reason. I haven't dug deep enough into futures in the async runtime to really figure out why it is.
The problem is that I think fundamentally it's any attempt of building a standardized layer like this has always captured the commonality at the time when the specification was made. So like WCI is a good example. It's like it solved exactly the problems that the 3-4 people that were interested in WCI at the time had, right? But then the world moved on and we had HTTP2 and we had server sent events, we had WebSockets, all that sort of stuff. And nothing of that was captured by WCI. And so the first framework that wanted to support this had to say, like, okay, screw the standard, I'm going to run my own thing again, right? And so every time innovation happens, these standardization layers are in the way. And now you have two choices, one of which is that you can only innovate by also modernizing the standard, and it works for very large standards like HTML. Or it's just like, well, it's just going to try it first. If it succeeds, we will standardize it after the fact. And if not, we just throw it away. And the second attempt of just standardizing after the fact often results in never standardizing at all because you're just going to stay with an ever-changing ecosystem of not standardizing. And this is what happens with Tokyo right now. I don't see Tokyo standardizing at all right now so that async STD can also use it because Tokyo wants to try new things and it doesn't have the capacity to also standardize the things that it wants to try.
Yeah, I think I kind of agree with that. I feel like Tokyo's they have the ability and the amount of people to try new stuff and to see what sticks and then gather info and then try to standardize from there. If I remember correctly, I think there's a push recently to make some more changes to futures recently. I don't know, you probably know more about this than I do, but I've seen something somewhere, some blog post somewhere that they're actually going to go back over the futures and try to do more things to it.
Yeah, I think async in Rust is going to change quite significantly again because people are discovering all kinds of things that need improvements. So we'll see where this goes.
Yeah, I really appreciate your library. I think it's not production ready, but I think it's got some interesting ideas to it. And it's good that it comes from somebody with production experience and headaches that you're coming at this with real world problems, right? So it's good to hear.
Yeah, it's mostly just an exploration phase. I would love people to sort of play with it and say, like, hey, this makes sense. It does make sense. Just to get a little bit of a diverse news set of eyes on it and see.
So if people want to check out this library, like, where do you think they should go? I mean, to me, I found it on Reddit. I think there's a pretty good explanation in there. You can also kind of go back and forth on there.
Yeah, at the moment, if you go to mitsuhiko/dser, like Serde in reverse, basically, or with the syllables switched, there's a README on GitHub that has sort of an overview. And there are a bunch of unit tests now and examples that show a little bit of how it works. And I also added a document to it, which is called sort of Serde learnings, which sort of explains some of the reasons why I'm exploring this at all in the existence of Serde. Oh, also one thing that should be added on this is that the design of Deezer is actually based on an alternative to Serde that was written by the original Serde author called Mini Serde. So the basic design of that library actually stems from Mini Serde to this attempt of a more runtime deserialization and more an alternative trait design that doesn't depend on exhausting the call stack so much. So worth pointing out that this actually doesn't entirely start on its own feet. It actually comes out of the design from the original author of Serde.
That's interesting. I'm curious why he didn't dig more into what you're working with than before this came out of the original design.
I think the problem with this design is that you're leaving some optimizations on the floor. And it's a massive depart. So one thing that should be said about both Mini Serde and Deezer is that the trait design that it exposes is impossible to use with safe Rust. So as an end user, you don't know because there's an abstraction in the system. It's called a driver that lets you use the library as if it was a safe library. But internally, it does some scary stuff to run the deserialization because it violates Rust rules. The borrow checker does not like what this library is doing. And for people that don't like unsafe code in their code base, that's probably not such a fun idea. So that's definitely one of the challenges with this is that there's unsafe code in it to make this thing work. And the second thing is that Mini Serde kind of sits in a very small space that's impossible to grow. So Mini Serde from its design cannot grow into Serde because it took some shortcuts that are inherent to its design. And Deezer is trying to bring back the Serde features on top of Mini Serde. But in order to do that, I had to make a lot of changes to it. Some of these changes hurt performance even more. And some of those changes, I'm not sure if they're so great. But yeah, it's just an interesting space to explore, I would say.
Yeah, I think the other thing too is like you're definitely more on the dynamic side rather than the statically compiled side, which is also like a big push. But yeah, okay. I know we're running out of time. I think I just kind of want to wrap this up very quick. Maybe you could just say, is there anything else that you want to say? And then we could have a couple last questions.
No, not much. Generally, I would love people to give feedback on this if they find it useful or if they had challenges with Serde. My goal is not so much to say like, hey, I want to build a Serde replacement. Really just let's see what else could there be and if it makes sense or not.
Okay, and then my last kind of question is like, do you have any kind of like tips or tricks that you want to give to beginners in Rust that can kind of help them on their journey? Some people have said like, don't worry about allocations or like things like this. Do you have any kind of tips or tricks?
Yeah, probably the same thing. It's like, don't be afraid of using reference counted wrappers if you don't like the borrow checker too much. I don't have any good tips and tricks, I think. I'm also using Rust long enough now to not run into every problem anymore. The one tip that I gave people, but I don't know how applicable it is nowadays, is basically to learn the things that you can't do in Rust and then just no longer do them. So this classic case of like, if you think, like, if your problem looks like borrowing adjacently out of a struct into itself, just don't do that. It doesn't work. And try to avoid these problems. Like, don't do the things that you can't express. Because if you're trying to express it and then only to go to, like, IRC or Discord afterwards to learn that you can't be doing this, you just wasted an hour, right? So if you don't even try to do these things, then it's a lot more productive.
Once again, you've surprised me with an answer that I wasn't ever expecting. So I never heard of something like that. And I'm also kind of curious to see what other designs and logos you've been putting out there for things I've been using, but maybe I'll find out another day. I appreciate your time, and it's good to hear that you actually done a lot more than just working with Python. And yeah, I really want to check out more about what you're doing with this, and let's see if this causes any kind of impact in the community. So thank you for your time.
Thank you for having me.